Right now, telescopes across the northern hemisphere are tracking 3I Atlas as it barrels toward its closest approach to Earth on December 19th, and the data streaming back contradicts nearly every theoretical expectation about how interstellar visitors should behave, leaving astronomers in a state of profound scientific unease. The object survived a close solar passage that should have vaporized it. Its brightness fluctuates wildly without pattern. Its trajectory has altered in ways that simple gravitational mechanics cannot explain. And extending from its nucleus are luminous structures stretching more than 1,000,000 kilometers into the void. Longer than the distance from Earth to the Moon, then doubled again and still continuing. Here's the problem. Comets are not built to endure what 3I Atlas has endured. Conventional astrophysics describes them as fragile aggregates of ice, dust, and frozen gases held together by weak cohesion. Cosmic snowballs that sublime violently when exposed to stellar radiation. When comet Ison approached the Sun in 2013, solar heat tore it apart completely. When Shoemaker Levy 9 grazed too close to Jupiter in 1994, tidal forces shredded it into fragments before it ever struck the gas giant's atmosphere. The catalog of disintegrated comets is extensive, well-documented, and theoretically sound. 3I Atlas did not disintegrate. Instead, it emerged from perihelion, the closest point in its solar orbit, structurally intact, and then began displaying behavior that has split the astronomical community into two incompatible interpretations. One camp, represented by Russian astronomer Alexander Kiselev, classifies the object as an exceptionally durable comet with physical properties that challenge outdated assumptions. The other camp, led by Harvard astrophysicist Avi Loeb, points to a constellation of anomalies that resist conventional explanation and may indicate something far stranger. The immediate question is not whether 3I Atlas poses a collision risk. Orbital calculations have ruled that out with high confidence. The question is what this object fundamentally is, and whether current comet models are inadequate, incomplete, or entirely wrong. Here's where it gets interesting. The photometric data, measurements of reflected light across multiple wavelengths, show that 3I Atlas has changed color during observation. Early spectroscopy revealed a reddish hue consistent with organic-rich tholins, complex molecules formed by ultraviolet radiation acting on simple carbon compounds. Later observations detected shifts toward bluer wavelengths, suggesting compositional changes on the surface, or the exposure of subsurface layers with different chemistry. This is not how inert bodies behave. Dead rock does not transform its optical signature within weeks. Then there is the brightness variation. Cometary outgassing typically produces predictable luminosity curves as volatile materials sublimate under solar heating, creating a diffuse coma that scatters sunlight. 3I Atlas exhibits brightness changes that correlate poorly with solar distance. At points where it should have dimmed, it brightened. At points where outgassing models predicted steady emissions, the light output dropped sharply. The variability suggests either an irregular nucleus rotating with uneven active regions, or processes occurring on or within the object that standard sublimation physics does not account for. Stop and consider that. If the brightness changes are driven by rotation, the nucleus must have extreme asymmetry, active geysers on one hemisphere, dormant terrain on the other. If they are not driven by rotation, something else is modulating the energy output. Both possibilities are scientifically uncomfortable. Now about the data concerning those million-kilometer structures. Ground-based observatories and space telescopes have captured images showing narrow, almost linear features emanating from the nucleus. To grasp the scale, 1,000,000 kilometers is roughly 2.6 times the Earth-Moon distance. If 3I Atlas were positioned where Earth orbits, and those rays pointed toward the Sun, they would extend well beyond the orbit of the Moon and approach the outer boundaries of Earth's magnetosphere. No known comet has produced anything remotely comparable in geometry or length. Avi Loeb has stated publicly that these features resemble neither a typical dust tail nor a traditional ion tail. Dust tails form when solar radiation pressure pushes microscopic particles away from the nucleus, creating broad, curved structures that lag behind the comet's motion. Ion tails are shaped by the solar wind, streams of charged particles from the sun that ionize gases in the coma and drag them into straight, narrow filaments pointing directly away from the sun. The structures observed around 3I Atlas do not conform cleanly to either morphology. They are too narrow and geometrically stable for a dust tail, yet too extensive and symmetrically arranged for a conventional ion tail. Loeb has proposed two interpretations. The first is that the rays represent an extreme form of material ejection, possibly subsurface volatile reservoirs venting through cracks or conduits in the nucleus, launching jets of gas and dust with unusually high velocity and directionality. The second interpretation is more provocative, that the observed features resemble exhaust plumes from propulsion systems, implying deliberate thrust rather than passive outgassing. Read between the lines. Loeb is not stating outright that 3I Atlas is an artificial construct. He is saying that the object presents more than a dozen unexplained characteristics within a short observation window, and that the hypothesis of non-natural origin cannot be dismissed on the available evidence. This is a carefully calibrated scientific position, one that invites investigation rather than conclusion. It is also a position that has drawn intense criticism from colleagues who argue that invoking artificial origins without exhausting natural explanations is methodologically premature. Alexander Kiselev offers a naturalistic counter-narrative grounded in material science and thermal physics. He argues that 3I Atlas is indeed a comet, but one whose surface has been profoundly altered by its interstellar history. Comets originating in the Oort cloud or analogous structures around distant stars spend millions of years drifting through the radiation-saturated environment of interstellar space. Cosmic rays, high-energy particles accelerated by supernova remnants and other violent processes, bombard the surface continuously, breaking chemical bonds and rearranging molecules. Over vast timescales, this irradiation could compact surface materials into a dense, refractory crust composed of silicate minerals and carbonaceous compounds resistant to sublimation. Kiselev likens this to sintering, a process used in industrial manufacturing where powdered materials are fused into solid structures through heat and pressure without melting. The result would be a hardened shell capable of insulating the interior from solar radiation far more effectively than the porous, loosely bound surfaces of short-period comets like Halley or Encke. Think about what that means for thermal modeling. Standard comet models assume that sunlight penetrates surface layers, heats subsurface ices, and drives sublimation that lifts dust and gas into the coma. If 3I Atlas possesses a sintered shell, solar energy would be absorbed or reflected at the surface, rather than conducted inward. Interior temperatures would remain low even at perihelion, drastically reducing outgassing rates. This could explain why the object survived solar proximity without fragmenting. It never experienced the internal thermal stresses that shatter ordinary comets. But here's where things get strange. If the surface is that well insulated, how do the million-kilometer structures form? Outgassing requires volatiles to escape, and volatiles can only escape if heat reaches subsurface reservoirs or if structural weaknesses breach the protective crust. Kiselev suggests that localized fractures, cracks formed by thermal expansion, tidal stress during stellar encounters, or micrometeorite impacts could provide conduits for pressurized gases to vent explosively. These jets, if narrowly collimated and sustained by high internal pressure, might extend to extraordinary lengths before dispersing. This explanation is plausible, but it requires the interior to be under significant pressure, which implies active sublimation despite the insulating shell. That creates a thermodynamic paradox. The shell must be thick and robust enough to prevent general outgassing, yet thin or fractured enough to permit localized jets. The balance required is delicate, and the longevity of such a configuration over multiple stellar passages is uncertain. There is also the matter of trajectory alteration. Preliminary orbital analysis indicated that 3I Atlas deviated slightly from the path predicted by gravitational influences alone. Such deviations are well documented in comets and are attributed to the rocket effect. Outgassing produces thrust that nudges the nucleus in the direction opposite the ejected material. The magnitude of the deviation depends on the mass of the nucleus, the rate of outgassing, and the duration of activity. For 3I Atlas, the observed trajectory change suggests sustained asymmetric outgassing. If the object is rotating and jets are firing from fixed locations on the surface, the net thrust vector would vary over each rotation cycle, potentially producing complex orbital perturbations. Calculating the exact effect requires detailed knowledge of the nucleus's mass, shape, rotation period, and the geometry of active regions, none of which are precisely known. Loeb has noted that the trajectory change, while consistent with the rocket effect, is also consistent with controlled maneuvering if the object were artificial. This is not evidence of artificiality. It is an acknowledgement that the data do not uniquely determine a natural origin. The scientific method requires that all hypotheses compatible with observations be retained until evidence excludes them. So far, no evidence definitively excludes either interpretation. Here's where the investigative pressure intensifies. If 3I Atlas is a natural comet with unusual but explicable properties, why has no similar object been observed before? The Oort cloud contains trillions of cometary nuclei. The Kuiper belt holds billions more. Interstellar space is populated with objects ejected from other stellar systems during planetary formation. Statistically, if sintered shell comets are common, observatories should have detected others by now. The fact that 3I Atlas appears unique suggests either that such objects are rare or that previous examples were misclassified or went unnoticed. Kiselev argues that the apparent rarity may be observational bias. Highly durable comets with low outgassing rates are faint and difficult to detect unless they pass very close to Earth or the Sun. 3I Atlas was discovered because it approached close enough and brightened sufficiently to trigger automated survey systems. Countless similar objects may have traversed the inner solar system undetected, their trajectories and properties lost to history. This raises an uncomfortable possibility. The population of interstellar visitors may be far larger and more diverse than current models predict. If the Oort cloud and its extrasolar analogs contain families of ultra-durable comets, alongside the fragile snowballs described in textbooks, the entire framework for understanding cometary origins, composition, and evolution requires revision. The implications extend to planetary science because comets are thought to have delivered water and organic compounds to early Earth, seeding the conditions for life. If cometary diversity is greater than assumed, the delivery mechanisms and chemical inventories must be reconsidered. The alternative interpretation that 3I Atlas is artificial carries implications of an entirely different magnitude. If the object is a probe, an artifact, or a derelict construct from another civilization, its presence in the solar system would constitute the first physical evidence of extraterrestrial technology. The scientific, philosophical, and societal consequences would be transformative. Loeb has emphasized that extraordinary claims require extraordinary evidence and that the current data do not meet that threshold. What the data do provide is justification for intensive follow-up observation. If 3I Atlas is artificial, close examination should reveal structures, materials, or behaviors inconsistent with natural processes. If it is natural, detailed spectroscopy, thermal imaging, and high-resolution photography should reveal surface textures, compositional gradients, and outgassing patterns consistent with cometary activity. The challenge is time. 3I Atlas is moving fast, and the observational window is narrow. After its December 19th closest approach, the object will recede rapidly, growing fainter as it travels outward toward the heliopause and beyond. Ground-based telescopes are already pushing their sensitivity limits to track it. Space-based instruments, Hubble, the James Webb Space Telescope, and upcoming missions are being petitioned for observing time, but scheduling conflicts and technical constraints limit availability. NASA's Planetary Defense Coordination Office has confirmed that the object poses no impact threat, which removes urgency from a public safety standpoint, but does not diminish the scientific stakes. The European Space Agency has expressed interest in coordinating multinational observation campaigns. Russia's Roscosmos has indicated that ground-based assets will continue tracking until the object exits viable observation range. China's National Space Administration has not issued public statements but is presumed to be monitoring independently. The lack of coordinated effort is frustrating to researchers who argue that 3I Atlas represents a fleeting opportunity. Unlike asteroids and short-period comets that return predictably, interstellar objects pass through the solar system once and vanish. Oumuamua, the first confirmed interstellar visitor detected in 2017, departed before comprehensive studies could be conducted, leaving behind unresolved questions about its shape, composition, and rotation. 2I Borisov, the second confirmed interstellar object discovered in 2019, was better characterized but still departed with mysteries intact. 3I Atlas is the third, and the pattern suggests that science is perpetually one step behind these transient phenomena. Loeb has advocated for rapid response missions capable of launching interceptors to rendezvous with interstellar objects while they remain accessible. Such missions would require propulsion systems capable of matching velocities with hyperbolic trajectories, instruments capable of close-range analysis, and launch readiness within weeks of initial detection. Current space agencies do not maintain such capabilities, though feasibility studies have been conducted. The financial and logistical barriers are substantial, but the scientific return could be unparalleled. A spacecraft that successfully intercepted 3I Atlas could deploy cameras, spectrometers, magnetometers, and particle detectors to characterize the nucleus in detail. Surface imaging could reveal whether the object exhibits natural cratering and erosion or geometric patterns suggestive of construction. Chemical analysis could determine whether the composition matches known cometary materials or contains elements, isotopes, or molecular structures foreign to the solar system. Even without a dedicated mission, ground-based observations can extract significant information. Radar observations, if the object passes within range of planetary radar systems like Arecibo's successor or Goldstone, could map surface roughness and detect subsurface layering. Infrared spectroscopy could measure thermal emission and constrain the temperature distribution across the nucleus. Polarimetry could reveal the size and shape distribution of dust grains in the coma, offering clues about surface weathering and outgassing mechanisms. The million-kilometer structures remain the most enigmatic feature. If they are indeed material ejecta, the particles composing them should exhibit spectroscopic signatures matching the nucleus. If they are ion tails, their geometry should align with the interplanetary magnetic field. If they are something else, optical artifacts, plasma streamers, or emissions from unknown processes, their characteristics should deviate from both models in measurable ways. Preliminary spectroscopy has detected emission lines consistent with ionized carbon monoxide and cyanogen, both common in cometary comas. This supports the natural outgassing hypothesis. However, the spatial distribution of these emissions is unusual. Typically, ions are concentrated in narrow tails extending anti-sunward. In 3I Atlas, The emission appears distributed across multiple filaments radiating in various directions, not all aligned with the solar wind. This geometry is difficult to reconcile with standard ion tail physics unless the magnetic field configuration near the comet is unusually complex, or unless multiple discrete sources are active simultaneously on different parts of the nucleus. Loeb has pointed out that multidirectional emission is consistent with thruster activity if the object were rotating and firing jets from fixed nozzles. Kiselev counters that rotating nuclei with asymmetric active regions naturally produce complex emission patterns as different jets rotate into and out of sunlight. Both explanations fit the observations, which means the observations alone cannot distinguish between them. This ambiguity is scientifically maddening. In most cases, additional data resolve uncertainties and converge on a single explanation. With 3i Atlas, additional data have amplified the range of plausible interpretations without eliminating any. Each new measurement adds detail but not clarity. Each refinement of the object's properties expands rather than narrows the solution space. Part of the difficulty is that interstellar objects carry no history beyond what can be inferred from their current state. A short-period comet like Halley has been observed over centuries, allowing astronomers to model its evolution and predict its behavior. 3i Atlas appeared without precedent, and its prior trajectory through interstellar space is speculative. Where it originated, how long it traveled, and what environments it encountered are unknown. Without that context, interpreting its current properties is like diagnosing a patient without access to medical history, possible, but fraught with uncertainty. Kiselev's hypothesis that prolonged irradiation in interstellar space produced a sintered crust is reasonable but unproven. Laboratory experiments have demonstrated that cosmic ray bombardment can alter the structure of ices and organics, but scaling those results to million-year timescales and comet-sized bodies involves assumptions about flux rates, particle energies, and material responses that remain uncertain. There are no interstellar comets in laboratories. There are no controlled experiments spanning mega-years. The hypothesis rests on extrapolation from limited data, which is the best that can be done but is not the same as empirical confirmation. Similarly, Loeb's hypothesis that the object might be artificial is logically sound but empirically underdetermined. The absence of obvious artificial features, radio transmissions, geometric regularity, metallic surfaces, does not preclude artificiality if the object is ancient, damaged, or designed to mimic natural forms. Conversely, the presence of anomalies does not prove artificiality if natural processes can, in principle, produce similar effects. The hypothesis is scientifically viable in the sense that it makes testable predictions. Closer examination should reveal unambiguous signs of construction if they exist, but those tests cannot be performed with current data. The tension between these interpretations reflects a deeper issue in observational astronomy, the problem of underdetermination. When multiple hypotheses are compatible with the same evidence, choosing among them requires additional assumptions, theoretical preferences, or appeals to simplicity. Occam's razor, the principle that simpler explanations are preferable, favors natural origins because invoking extraterrestrial technology introduces entities and complexities not otherwise required. But Occam's razor is a heuristic, not a law. Nature is not obligated to be simple, and history is filled with phenomena that seemed impossible until they were observed. What is known with confidence is that 3i Atlas will make its closest approach on December 19th. At that point, the object will be approximately 0.3 astronomical units from Earth, roughly 45 million kilometers, or about 30% of the Earth-Sun distance. This is close enough for large observatories to achieve relatively high angular resolution, though not close enough for surface details to be visible without adaptive optics or space-based imaging. The days surrounding closest approach will be critical. Observatories in North America, Europe, and Asia are coordinating schedules to ensure continuous coverage. Amateur astronomers with sufficiently large telescopes are being encouraged to contribute observations, expanding the data pool and increasing the likelihood of capturing transient events like outbursts or sudden brightness changes. Kiselev has predicted that 3I Atlas may undergo increased activity as it approaches Earth, not because of proximity to our planet, but because the timing coincides with its trajectory through the inner solar system where solar heating remains intense. If the sintered crust has fractures, thermal expansion during approach could widen those fractures, allowing more volatiles to escape and potentially brightening the coma. Loeb has suggested that if the object is artificial and still functional, proximity to Earth might trigger responsive behavior, activation of dormant systems, changes in orientation, or transmission of signals. He has called for radio telescopes to monitor the object across multiple frequencies, listening for coherent emissions that would indicate deliberate communication or residual electronic activity. The Breakthrough Listen Project, a privately funded initiative to search for signs of extraterrestrial intelligence, has allocated observing time on the Green Bank Telescope in West Virginia to scan 3I Atlas for radio emissions. Initial observations detected no signals above background noise, but monitoring will continue through the close approach and beyond. If the object emits nothing, it proves nothing. A derelict probe might be inert. A functioning probe might operate outside the radio spectrum. A natural comet emits no radio signals except plasma noise from ionized gases, which has already been detected and is consistent with cometary activity. The absence of evidence is not evidence of absence, but it does shift the burden of proof toward those claiming anomalies require non-natural explanations. The outcome of the December observations will shape the debate. If high-resolution imaging reveals surface cratering, layered terrain, and other features consistent with natural accretion and weathering, the case for a comet, albeit an unusual one, strengthens. If imaging reveals geometric patterns, smooth surfaces, or structural regularity inconsistent with random accumulation, the case for artificiality strengthens. If imaging reveals nothing conclusive, the debate will continue unresolved until the object exits observation range, leaving the question open indefinitely. Kiselev has expressed confidence that 3I Atlas will eventually be understood within the framework of conventional comet science, even if that framework must be expanded to accommodate objects more durable and compositionally diverse than previously recognized. He notes that the discovery of exoplanets forced revisions to planetary formation models, and that the discovery of ultra-durable interstellar comets similarly requires updating models to reflect new observational realities. He has also reiterated his prediction regarding the object's ultimate fate. Regardless of whether 3I Atlas is natural or artificial, its long-term survival is unlikely. Each stellar passage erodes its mass through outgassing or ablation. Each transit through interstellar space exposes it to micrometeorite impacts and radiation damage. Over timescales measured in millions or tens of millions of years, the cumulative degradation will either reduce it to an inert core, devoid of volatiles, or fragment it entirely through collision with another object. The first scenario, gradual depletion into dormancy, transforms the comet into something resembling an asteroid, a dark, rocky body with negligible activity. Such objects are difficult to detect and easily overlooked. Surveys of the asteroid belt have identified numerous bodies with cometary characteristics, suggesting they are extinct or dormant comets that exhausted their volatile inventories. 3I Atlas may follow the same trajectory, eventually becoming indistinguishable from the background population of small solar system bodies. The second scenario, catastrophic fragmentation, is statistically more probable. Space is not empty. The solar system contains billions of asteroids, comets, and meteoroids. Interstellar space is less dense, but still populated with debris. A collision with even a small object traveling at high relative velocity could shatter 3I Atlas into fragments ranging from boulders to dust. The resulting debris would disperse along the object's trajectory, eventually becoming undetectable. If destruction occurs, it might be observable. The impact would release energy proportional to the kinetic energy of the collision, potentially producing a bright flash and a sudden increase in dust emission. Ground-based surveys designed to detect transient events might capture such an occurrence, though the probability of observing a random collision is low given the vastness of space and the brevity of human observation. There is a third, rarely discussed scenario: intervention. If 3I Atlas is artificial and still operational, it might take actions to avoid destruction, course corrections to evade hazards, deployment of shields or countermeasures, or even self-repair. If such actions were observed, they would constitute unambiguous evidence of artificiality. Conversely, if the object is artificial but inert, it remains subject to the same destructive forces as any natural body, and its eventual disintegration would erase the evidence of its origin. This is the fundamental frustration. If 3I Atlas is a probe and it disintegrates before being studied, the opportunity to confirm extraterrestrial technology is lost irreversibly. If it is a natural comet and it escapes detailed observation, the opportunity to understand a new class of cometary objects is similarly lost. Either way, the window for investigation is narrow, the stakes are high, and the resources allocated are insufficient to guarantee success. The broader scientific community remains cautiously engaged. Major journals have published preliminary analyses, and conferences have featured sessions on interstellar objects. Funding agencies have received proposals for follow-up studies, though the competition for grants is intense and priorities are divided among many research areas. The public, meanwhile, oscillates between fascination and indifference depending on media coverage, which tends to favor sensational interpretations over nuanced uncertainty. Loeb's willingness to discuss artificial origins has drawn both praise and criticism. Supporters commend his intellectual courage and argue that science advances by challenging assumptions, not by clinging to comfortable paradigms. Critics accuse him of speculation beyond the evidence and warn that premature claims of extraterrestrial technology undermine public trust in scientific rigor. The debate mirrors historical controversies. When pulsars were first detected in 1967, their regular radio pulses seemed so artificial that astronomers briefly considered the possibility of alien transmitters, even assigning the designation LGM-1 for little green men. Further analysis revealed pulsars as rotating neutron stars, natural phenomena governed by electromagnetism and angular momentum. The episode demonstrated the importance of exhausting natural explanations before invoking extraordinary ones, but it also showed that scientists seriously consider unconventional hypotheses when data warrant. 3I Atlas occupies similar conceptual territory. The data are strange, but not definitive. The explanations are plausible, but not conclusive. The stakes are significant, but not immediate. Science proceeds by accumulating evidence, testing predictions, and refining models. The process is slow, often frustrating, and rarely delivers the clear-cut revelations that popular narratives prefer. Yet the mystery persists, and with it, the questions that refuse easy answers. If 3I Atlas is a comet, why does it deviate from models that successfully describe thousands of other comets? If it is a product of interstellar evolution, why has no similar object been detected before? If it is artificial, why does it exhibit cometary activity? And why has it not transmitted signals or altered course in ways that unambiguously reveal deliberate control? Each question opens onto others. If ultra-durable comets exist, how many traverse the solar system undetected each year? If interstellar space can sinter comet surfaces into protective crusts, what does that imply for the survival of organic molecules during interstellar transit, and consequently for panspermia, The hypothesis that life propagates between star systems via cometary delivery? If extraterrestrial civilizations construct probes and send them into the galaxy, how many such probes currently drift through the solar system mistaken for natural objects? The proximity of 3I Atlas offers a rare chance to address some of these questions. The object is close, bright, and observable with existing instruments. It will remain accessible for weeks, allowing multiple observations across different wavelengths and techniques. The data collected will inform models, constrain hypotheses, and potentially resolve or deepen the mystery. But the clock is running. December 19th is approaching. After closest approach, 3I Atlas will accelerate outward, driven by its hyperbolic trajectory and whatever forces, gravitational, thermal, or otherwise, act upon it. The distance will grow, the brightness will fade, and the window will close. Observations that are not made now will never be made. Questions that are not answered now may remain unanswered indefinitely. Astronomers are acutely aware of this temporal pressure. Observing proposals are being submitted with urgent language. Telescope time is being negotiated and reallocated. International collaboration is being invoked to maximize coverage and data sharing. The scientific apparatus is mobilizing, but whether the mobilization is sufficient remains uncertain. There is also the matter of public communication. Should the discovery of compelling anomalies be announced immediately, or should results be withheld pending peer review and independent confirmation? Immediate disclosure risks spreading premature conclusions and fueling misinformation. Delayed disclosure risks accusations of secrecy and erodes public trust. The balance is delicate, and different institutions have different policies. Loeb has argued for transparency, stating that the public has a right to know about significant findings as they emerge, especially regarding questions of extraterrestrial intelligence. Kiselev has emphasized the importance of rigorous analysis before making claims, noting that hasty announcements can damage scientific credibility and distract from the careful work required to understand complex phenomena. Both positions have merit, and the tension between them reflects the dual role of scientists as researchers and communicators. The imperative to seek truth and the imperative to inform society are not always aligned, and navigating the gap requires judgment, integrity, and an awareness of the broader impact of scientific discourse. As December progresses, the world will watch, or not. Media attention will spike around the closest approach, then dissipate as newer stories emerge. The scientific community will continue its work regardless, driven by curiosity, methodological commitment, and the recognition that understanding the universe is a cumulative, multi-generational effort. 3I Atlas will pass, recede, and eventually vanish into the interstellar darkness from which it came. Whether it leaves behind answers or deeper mysteries depends on what the data reveal and how those revelations are interpreted. The object itself is indifferent to human curiosity. It does not perform for observers or yield its secrets on demand. It simply is, whatever it is, moving through space according to the laws that govern all matter, natural or otherwise. The question that will linger, long after the observations conclude and the papers are published, is whether those laws are sufficient to explain what has been seen. If they are, 3I Atlas becomes a milestone in cometary science, proof that nature harbors diversity beyond current models and that interstellar space forges objects with properties unanticipated by theory. If they are not, the implications cascade outward, touching every field from astrobiology to engineering, philosophy to policy. Think about what that means, not in abstract terms, but concretely. If 3I Atlas is confirmed as artificial, it proves that technological civilizations arise elsewhere in the universe, that they build and deploy objects capable of interstellar travel, and that at least one such object has entered the solar system. It proves that humanity is not alone, that intelligence is not unique to Earth, and that contact, even indirect, through the discovery of an artifact, is possible. It also raises immediate practical questions. Where did the object originate? When was it launched? Is it functional or defunct? Are there others? Should humanity attempt communication, retrieval, or study? What protocols govern the handling of extraterrestrial technology? Who decides? These questions have been debated in academic and governmental contexts for decades, often hypothetically. The discovery of an actual artifact would transform the debate from theoretical to operational, demanding decisions with profound consequences. Conversely, if 3I Atlas is confirmed as natural, it still reshapes understanding. It demonstrates that comets can be far more resilient than assumed, that interstellar environments can dramatically alter surface properties, and that the diversity of small bodies in the galaxy exceeds what solar system observations alone reveal. It suggests that the Oort cloud and its analogs around other stars contain populations of ultra-durable objects that represent a distinct evolutionary path. It implies that the delivery of water and organics to planetary surfaces during the early epochs of stellar systems may involve not just fragile icy bodies, but also hardened, long-lived carriers capable of surviving violent impacts. Either outcome is scientifically valuable. Either outcome expands the boundaries of knowledge. But one outcome also expands the boundaries of reality as currently understood. And that possibility, however remote, however uncertain, justifies the intensity of scrutiny being directed at a single, fast-moving object millions of kilometers away. The instruments are ready. The observers are prepared. The calculations are refined. December 19th will arrive, the distance will shrink to its minimum, and the data will flood in. Photons captured by sensors, wavelengths analyzed by spectrometers, positions tracked by astrometry. The machines will record what they detect without bias or interpretation. The analysis will come later, conducted by scientists who bring their expertise, their assumptions, and their questions to the task. And then, perhaps, clarity. Or perhaps more questions. Perhaps confirmation of the familiar, or revelation of the unprecedented. Perhaps closure, or the beginning of a deeper investigation that spans years and involves missions not yet designed. But those outcomes lie ahead, contingent on observations not yet made. What exists now is potential. The potential for discovery, for surprise, for paradigm shift, or incremental refinement. The object moves, the Earth turns, and the distance between them narrows, according to the predictable mechanics of orbital motion. What is not predictable is what the final analysis will conclude. The data will be what they are, but their meaning remains contested, and the contest is not merely academic. It is a struggle to understand what exists beyond familiar categories, to reconcile the seen with the expected, and to decide when evidence is sufficient to overturn long-held beliefs. Kiselev believes the evidence points toward a natural, if extraordinary, comet. Loeb believes the evidence justifies considering artificial origins. Both are scientists of standing. Both have analyzed the same data, and both have reached different conclusions. This is not a failure of science, but its normal operation. Disagreement drives investigation. Uncertainty motivates observation. Mystery is not an obstacle, but the condition that makes discovery possible. So as 3I Atlas hurtles onward, the real question is not whether it will be explained. Eventually, it will be, in one framework or another. The real question is what that explanation will require science to accept. A new class of comet or a new class of object entirely. A refinement of existing models, or a revision of fundamental assumptions about what exists in the cosmos and who, or what, might have made it. If the data streaming back on December 19th confirm every expectation, the mystery fades and 3I Atlas becomes a footnote, an unusual comet, rigorously studied, correctly understood, and filed away in the catalog of celestial phenomena. But if the data defy expectations, if the observations refuse to align with natural processes, no matter how creatively those processes are modeled, then the mystery deepens into something more unsettling. Because at that point, the question is no longer what is 3i Atlas? The question becomes, if this is what it appears to be, how many others are out there, moving through the dark, unnoticed and uncategorized, carrying histories and purposes we have yet to imagine? And if that question has an answer, if the universe is populated not just with rocks and ice but with relics, constructs, and emissaries from civilizations scattered across the galaxy, then the implications extend far beyond a single object observed for a few weeks in December. They extend to the very nature of cosmic reality and humanity's place within it. The instruments are aimed. The observations will proceed. The mystery, for now, remains unresolved. And perhaps that is fitting, because the edge of knowledge is precisely where the most important questions arise, where certainty gives way to wonder, and where the familiar cosmos reveals itself as stranger, vaster, and more full of possibilities than the mind can easily